Hey, yo, Chemsters, this is Mrs. Vandaloy bringing you 10.2, and I'll also do 10.4 today. So 10.2 is the physical properties of carboxylic acids. And to me, the most obvious physical property of carboxylic acids is their smell. You remember me telling you in section 10.1, when I was telling you about acetic acid, when we buy acetic acid for the high school, it comes as that glacial acetic acid. And boy, am I telling you, it stinks. Do not, and I repeat, do not ever open up glacial acetic acid unless it's under a hood. All right, you think that the vinegar you buy in the store is potent? Oh, this is a lot worse. Okay, so and I have acetic acid. What you buy in the store is 4 to 5% vinegar, so 96, 95% water. So it's truly watered down. Glacial acetic acid is much more concentrated and it smells that way too. Earlier we talked about rotten butter, rancid butter, and so people 100 years ago didn't have the refrigeration that we have now, so their butter would go bad a lot sooner. I don't know if you've ever smelled bad milk, and that's where your lactose becomes lactic acid. Well, similar things happen with butter. Okay, so the saccharide of your butter becomes an acid. Okay, and it becomes butyric acid, or as we would know as butanoic acid, and it smells bad. Most folks today don't know what that smells like. I can't say I know what rancid butter smells like. I do know what rancid milk smells like, though. Well, guess what? Goat acids, well, yes, they actually smell like goats. All right, surprise, surprise. Do you remember back in the last chapter, didn't we, or the last section, we had 3 acids. The hexanoic, octanoic, and decanoic acids are all from your goats. So that's 3 acids they put out there, okay? Now, me, I really don't know what a goat smells like, but I know what a barnyard smells like, all right? It's not something I want to put in my air freshener. I don't know about you. All right, so anyway, yeah, goats smell like, well, goats, okay? Do me a favor, pause this for a second and sketch out 3-methyl-2-hexenoic acid. Do that for me. All right. I don't know if you're done, but I'm done. This is what I got. So here's my hex. I have 6 carbons right here. And notice on carbon number 1, I have the C double bond OOH. And then here's carbon number 2. I have my double bond. All right. And then off of carbon 3, I have my methyl group. Well, guess what this is? Well, yeah, something doesn't smell too good. All right. This is body odor. Yep. BO. Okay. So I'm sure you all know what BO smells like. It's not a pleasant thing. And notice once again, we have a carboxylic acid going on. So if I haven't convinced you yet, hopefully I now have convinced you that carboxylic acids are rather smelly, aren't they? Well, what are some physical properties we can talk about? Well, let's find out. All right, so carboxylic acids are actually quite polar. Let me scroll down a little bit. See these oxygens right here? You got 2 oxygens actually in close proximity. All right, so that makes carboxylic acids polar. Now, let me just say one thing real quick. The longer the carbon chain, the less polar it is. So the shorter the carbon chain, really the more polar it is, all right? So if you have fewer carbons, then you really have this true region of partial negative and a short region of partial positive, okay? But because they are polar, guess what? They form London dispersion and, yes, dipole-dipole because they're polar, but not only dipole-dipole, they form hydrogen bonds because of right here. You have the H off the O, but you have 2 O's here, okay? So guess what? They have high boiling points, and they have even higher boiling points than comparable alcohols. Alcohols have hydrogen bonds we learned in the last chapter. Well, so do these. But why are they even higher? It's because it's even a more polar bond. You have 2 oxygens right here instead of 1, okay? So look at these. They have the same molecular weight of 60 grams per mole, all right? But yes, ethanoic acid is over 20 degrees higher boiling point than propanol, all right? So that shows me they have very high boiling points. Well, here's a couple other physical properties that you can look at. They're very viscous. All right, for the last time, I'll tell you a little bit about this glacial acetic acid. When I pour it out to make acetic acid, I usually don't ever have glacial acetic acid by itself. However, in the ester lab that is coming up, you will see this glacial acetic acid, and we keep it in the hood. All right, it is viscous. That means it's thick. It's almost the consistency of like vegetable oil. Vegetable oil is non-polar but very massive. All right, that makes it viscous. This isn't nearly as viscous, nearly as high molar mass as an oil, but because of those hydrogen bonds, it does adhere to each other and it is viscous, okay? It's also dense or denser when compared to other similarly massed functional groups, okay? All right, so those are the main properties you ought to know about carboxylic acids. You'll never forget they smell bad, right? So what else do we want to talk about? What makes carboxylic acids acidic? Now you might want to jot this down. Depending on what you remember from your first year chemistry class, what's an acid? All right. The common definition that we will use is that an acid is going to donate its hydrogen. All right. Which one? There's lots of hydrogens. All right. Look at all the hydrogens over here. Those don't count. It's this hydrogen that we're looking at. So this hydrogen that's attached to the oxygen, we want to look at as far as being an acid. So how likely is this H going to break off of the O? The more likely it's going to break off, the better the acid. The more stronger the acid, all right? The more tightly bound the H is to the O, the weaker the acid, okay? So let's go back down here again. So one way to determine the strengths of acids is to look at their Ka values. The larger the Ka, the stronger the acid. And there are two reasons. And the two reasons, we're going to look at the ethanol itself, and then we're going to look at the ethanoic acid. And so we're going to see why that will be. Okay, well, let me just show you something. Notice I did put the partial negative, partial positive on here. So that kind of gives you the idea that, yeah, it's a polar bond. All right, but how strong is the O and the H? Well, this Ka tells me something. So the larger the Ka, the stronger the acid. So the larger the K value, the more likely the H is going to come off, okay? So this Ka value here tells me how much is going to fall off, okay? Let me show you something. What I have shown you are the Ka expressions themselves. So you define the Ka as your concentrations of your products over your concentration of your reactants. So what this is saying is that this value is equal to 10 to the negative 16th. So think about this. If it's 10 to the negative 16th, your numerator is really small and your denominator is really big. Okay, so what does that mean? How many H pluses do we have? A really small number. How many intact ethanol molecules do we have? We have a lot, okay? Well, look at down here. Ka is equal to 10 to the negative 5th, all right? It is still classified as a weak acid, but not nearly as weak as this. What does this mean? That this is 10 to the 11th or 100 billion times stronger of an acid than ethanol. So why is that? Well, we'll explain in a minute, but real quick, what does this mean? That there is really 100 billion times more of these formed than up here. We have a whole lot more H pluses here than we do here, okay? So that makes ethanoic acid a stronger acid, because you make a lot more of H pluses as you do up here, okay? Now, why is that? I'm also giving you a preview here, and I want to show you something. Let me extend the page. There we go. So what's happening here is that if you recall, here I have the acetyl bond OH. Here's my other carbon. This is an sp2 hybridized. This is trigonoplanar. The bond angle here is really 120 degrees. I know my smartboard doesn't really show it, but in reality, it's about 120 degrees. All right. I have two oxygens here, making this a very large electronegative all right, area kind of shared between these two oxygens, and here's my H plus. If we want to talk about bond strength, okay, if this is a weaker bond, the H is going to come off. If it is a stronger bond, it's not more likely to fall off. And what causes that? Well, where are the electrons? The electrons are actually closer to the oxygen because the electronegativity value weakening the bond. Let's see what I'm talking about. Okay, whoops. Where is it? There we go. All right. So in ethanol, the carbonyl carbon, that's this carbon right here. Notice it's not a carboxyl carbon, it's a carbonyl carbon, carries a substantial partial positive charge. So the carbons down here are partially positive. Okay, think about this. This makes it easier to place the negative charge on this oxygen. So in the F oxide ion, the negative charge is localized on a single oxygen atom. So what does this mean? Here's my ethanol. If it donates, see, I got rid of my H plus, what remains? All right, what remains is the F oxide ion, and now the full negative charge is on the oxygen. But what about an ethanoic acid? All right, more stably, the acetic acid. All right, see, yeah, sorry, the acetate ion. Do you remember? Let me show you some real quick. Let me go back to the prior page. I know you all know what acetate is. Remember that was C2H3O2 negative. Remember that? Look at this, C2H3O2 negative. The acetate ion is what remains after the H is gone. Okay, so here is my acetate ion. Watch, the negative charge is spread equally over the two oxygen atoms so that each oxygen atom on the acetate ion carries only half the negative charge. Because this negative charge is distributed between these two oxygens, it makes it more stable. I'm going to make an analogy. Back in, a few chapters ago, we learned about the stability of the carbocation. That's when we're talking about the Markovnikov rule, okay, when we're talking about the addition of your alkenes and alkynes, all right? So do you remember what made a more stable carbocation as if it was a tertiary? It has more carbons to spread the H plus around, making it more stable. All right, so an analogy would be, well, the more oxygens you have, the more it can share that negative ion, making a more stable ion. All right, so we're saying putting A and B together, the end result is that the positive charge is on the carbonyl carbon, and the delocalization of the acetate ion, the carboxylic acids are much more acidic than alcohols, meaning on this page, we're talking about the stability of the ion. The acetate is much more stable than the F oxide ion because of its ability to share it. On the prior page, another thing is looking at the electronegativities and how it is sharing in the sense that that negative charge, making the bond weaker in the ethanoic acid than with the ethanol, okay? So bottom line, all right, carboxylic acids are gonna more easily give up its H plus. And folks, I'm at the end of 10.2 and 10.4, so don't wait to be great. We'll see you next time. Bye-bye.